So we've looked at the first translation theorem, which dealt with translations in S space. And now we'll look at the second translation theorem, which deals with translations in T space. Okay? And we'll also need to consider the unit step function since we're looking at translations in T space. The reason is that suppose you have this function f and you translate it a units to the right. Okay, so this is here, it's just copied here in pink. Well, what are you going to do with all that space that was there? Why not just set it to 0? And the unit step function will help us to do that. Okay, so it's an essential part of talking about T translations. What is the unit step function? The unit step function, or often called Heaviside function, okay, especially in physics, it's just referred to as the Heaviside function. It shows up all over the place, actually. It's pretty straightforward, okay? It's defined as 0 when t is greater than or equal to 0 and strictly less than a, and 1 when t is greater than or equal to a. Okay, so here, and we could just emphasize that at a, it's equal to 1. Okay, and you could have a hole there. All right, that's the unit step function. Simple. It's also called the Heaviside function. And like I said, despite its simplicity, it actually shows up all over the place. I mean, in quantum field theory, for example, the Heaviside function is used extensively. So something to note here too is that if you have a piecewise defined function like this, you could frame it in terms of the unit step function. Okay, so at a, this becomes 1, right? So you'll get this g of t, this term becomes non-zero, and then just subtracts with that. So before a, okay, when t is strictly less than a, then you get that this term is 0 and this term is 0, and so g of t is the only thing that's on, if you will. And then right at a, this turns on, canceling this and leaving you with this, which is the h of t. Okay, so it's a nice way to write piecewise defined functions. Similarly, if we have a piecewise defined function where you start 0, you turn on some impulse, if you will, g of t, between a and b, and then you turn it off. Okay, so 0. Then you could write this piecewise defined function this way. Okay, this will be on between a and b, and then turn off outside of those. So let's look at an example, concrete example of doing this, looking at piecewise functions and framing them in terms of the unit step function. So we have f of t here. Okay, it's 20t from 0 to 5, and then at 5 and greater, it's 0. And how do we put this in terms of the Heaviside function? Well, we have this 20t. That's on when t is strictly less than 5, but when t becomes 5 and greater, this term turns on, and 20t cancels 20t there for t is greater than 5, so it becomes 0. Okay, so just a straightforward way of using the unit step function to frame piecewise defined functions. So now we're ready for the second translation theorem. And if we have that if the Laplace transform of lowercase f is capital F for this domain and a is a positive constant, then when we translate lowercase f a units to the right and we fill in everything to the left of the translation with 0, okay, that's the role of the unit step function, we get that the Laplace transform of this is equal to the Laplace transform of just f with e to the negative as, okay? And now you could contrast that with the first translation theorem, which we've looked at before, where we applied e to the at to f and then Laplace transform to get the translation in the s space. Now we translate in t space and then get e to the minus as times fs, okay? Alternatively, we may write this in the form of gt with the unit step function, so this not translated, but then the translation just happens in here, okay? G of t plus a of the Laplace transform of gt plus a, so instead of here, it's here. That could help us in some situations. In the inverse form, we could just write that, you know, the inverse Laplace transform of this is equal to this, basically. That's what we have here, okay, where the inverse Laplace transform of capital F is f, okay? So that's inverse form. Let's compute some Laplace transforms. Let's start with the unit step function, okay? Here, we're just going to choose that f of t equals 1. And if you take the constant function and you translate it a units to the right, it's still the constant function 1. And so we have that the Laplace transform of this, which is what we're trying to solve, is equal to this, okay? And so we, using this theorem, we have that the Laplace transform of u of t minus a is going to be the Laplace transform of lowercase f, which is 1 here, times e to the minus as. And we know the Laplace transform of 1, it's 1 over s, and so we get that. Another simple example here is to find the Laplace transform of f of t, where f of t is defined using the unit step function. And we just apply the Laplace transform, and we still have linearity, right? And since we know the Laplace transform of the unit step function now, we just use what we computed here before. Here, a would be 2, so we get this negative 2s, because we have a negative there. This here would be, a would be 3, and so we get that. We get the 1 over s because of that relation there. So let's look at another example. We want to compute the Laplace transform of sine 4t, u to the t minus pi over 2. Now what's the problem here? The problem is that we're not given a function that's framed in the language of translation, okay? This here has t minus pi over 2, but that sine 4t, we don't see a t minus pi over 2 in there. If you look at the theorem, it has ft minus a there. Okay, so something you could do is rewrite this sine 4t in terms of the translation. So sine of, say, x plus 2 pi or x minus 2 pi is just going to be sine of x. That just means, you know, the periodicity of sine and cosine is 2 pi, so translating to the right or left with 2 pi gets you the same thing. So we're just going to go ahead and do that. And now notice that if we factor a 4 out of this term, we get t minus pi over 2. And so that's nice because we can now frame this in terms of the translations of pi over 2. So we get that this is equal to the Laplace transform of this, just by straightforward, you know, manipulation. And now it is framed in the language of the theorem, and we just apply the theorem. We know that this will give you, since a is pi over 2, we get a negative pi over 2 times s, e to the negative pi over 2 over s there. That's this term here. And the Laplace transform of the function, sine 4t, we know what that is from basic tables, it's there, and so we're done. Let's look at another example. So this. Now, what if we don't want to frame this using the translation of t minus pi? Okay, so we don't want to recast this as cosine of t minus pi somehow, or some other transformed, some other function that we get in terms of t minus pi, okay? If we could recast cosine t as some other function with t minus pi, okay? It doesn't necessarily have to stay sine as we had, it doesn't have to stay cosine as we had up here where it stayed sine. Okay, but okay, say we don't want to do this translations. Then we could use the alternate form, okay? The alternate form has this, okay? G of t plus a, okay? And note that cosine of t plus pi is negative cosine of t. And so what we could do is have the Laplace transform of cosine t times the unit step function translated is equal to e to the minus pi s, why pi, because a is pi, okay? And now we get this cosine t plus pi, again, just applying this right here, okay? So we've translated cosine to t plus a, or t plus pi in our case. And what is cosine t plus pi? Okay, it is negative cosine t. And so that's straightforward to take the Laplace transform of. We could take out the minus sign due to linearity, and we know the Laplace transform of this, so we get this result right here, okay? This here is the Laplace transform of cosine t. All right, so let's use the second translation theorem to solve a differential equation. Here's a first order differential equation. We have a piecewise defined function. Okay, it'll be a great idea to reframe it in terms of the unit step function. We have this initial condition. So this initial value problem is it's a good idea to try to solve this using the Laplace transform. So we first frame f in terms of the unit step function. We apply the Laplace transform. We've computed the Laplace transform of this in the previous example. Okay, the right-hand side, the non-homogeneous term, that's this right here. Okay, and that 3 is just coming from there. And here's the Laplace transform of the derivative. The derivatives, this over here, the left-hand side. And we then solve for ys. When we solve for ys, we get this term here. And again, we apply partial fraction decomposition on this over here and distribute the e to the pi s to get that. Okay, and this stayed the same. And all right, we have our capital YS. We solved it algebraically. We put it in we used partial fractions in order to easily apply the inverse Laplace transform and take advantage of the linearity property. And so now we just apply the inverse Laplace transform, take advantage of the linearity property, and in inverse form we have this, okay? And so we have this e to the negative pi s, and so we get this, we identify a with pi, and so we'll transform 1 over s plus 1 here to e to the minus t minus pi, okay, with the unit step function. We then apply the inverse Laplace transform with this, noting this translation factor, if you will, and we get that the inverse Laplace transform of 1 over sine squared plus 1 is just sine of t, but because of the translation factor there, we're going to get the unit step function and sine translated. And finally, the same for this. This is an S, and I'll write that, make it a little clearer. Okay, and again, we get that term there. And then we could just factor out some common terms, the unit step function common term, and we get this. And we could put this in terms of piecewise defined functions. And we get this expression there for the solution to this differential equation, okay? So that's nice. The Laplace transformed allowed us to work with piecewise defined functions more easily because we have the Laplace transform of the unit step function. And this was an initial value problem, so the Laplace transform helps with those. It actually includes the initial conditions in terms of the Laplace transform of the derivatives. And so this is a prime kind of problem that's best solved using the Laplace transform. Finally, here's a problem with a physical application here. So if you have a uniform beam of length L carrying load W, okay, so just a weight being applied, has deflection yx that obeys this differential equation there, where E is Young's modulus and I is the moment of inertia of a cross-section of the beam. So you can see here that the weight is applied here. There's greater weight, lesser weight, lesser weight, lesser weight, and then it goes to 0 for this load, okay? That's why it's a function of x. And this will cause deflection, okay, yx. And this is a piecewise defined function, so why not solve this using the Laplace transform? We could frame the load in terms of the unit step function. We get this expression here. We apply the Laplace transform, okay? Now, we have boundary conditions here, okay? That y0, the deflection, because it's attached to the wall over here, there is no deflection at the wall. So a y of 0, and it's also not moving at the wall, and y prime of 0 is 0, and so is yl and y prime of l, okay? So at the wall, there is no deflection, there's no change in deflection, and so that's 0. And we actually have some wiggle room with the second derivative and the third derivative. So we're just going to set those to constants, okay? We're just going to set those to constants, and you'll see why in a second. So using this, we solve for ys. We get this expression there, okay, once we simplify. And then we apply the inverse Laplace transform, okay? And we actually input. So when we did the Laplace, this was 0, this is 0 by this boundary condition. We still have not put this boundary condition, all right? And we set the second derivative and third derivative at 0 here to C1 and C2. So applying the inverse Laplace transform, we get this. And now why did we choose to keep our wiggle room with the second derivative and the third derivative and just set them to C2 and C1 over here and here? It's because now we'll apply the second boundary condition, okay, that we see here. So we apply these two boundary conditions, we get these equations, which give us C1 and C2, and we end up with this final solution once we substitute for C1 and C2. Okay, this is a fourth order equation, and so that's what gave us the wiggle room to do this, and eventually find C1 and C2 by applying these boundary conditions. So these are the actual boundary conditions that we used.